Hello everyone. Let's continue solving the problems of the chapter 2. Problem 14. A single phase 25 kVA 220 to 440 volt 60 Hz transformer gave the following test results. Open circuit test. The high voltage side is open. This is the voltage of the open circuit, the current of the open circuit test, and the power loss in the open circuit test. That is for the core loss. In the short circuit test, the low voltage side is shorted. This is the voltage of the short circuit, the current, and the power loss. So, A. Derive the approximate equivalent circuit in per unit values. B. Determine the voltage regulation at full load, 0.8 power factor lagging. C. Draw the phasor diagram for condition B. Okay, before answering this problem, let's review the per unit system from the textbook. Here in this section 2.8, we have a per unit system. Let's review definitions. Computations using the actual values of parameters and variables may be lengthy and time consuming. However, if the quantities are expressed in a per unit system, computations, right, are much simplified. We saw this when we generated these vector diagrams, for example, when I run this code. Here, because the value of the voltage is much higher than the value of the current, we need to specify a proper scale to draw this vector diagram. Even for computations, when we refer quantities of a transformer from the high voltage side to the low voltage side, we have change in amplitudes. But how we can define a per unit system to properly scale quantities for better visualizations, right? Phasor diagrams, even better computations. Yes, we don't need actual values, and sometimes phase differences is more important. Okay, so here is the definition of a per unit quantity. The per unit quantity is defined as follows. The quantity in per unit is actual quantity divided by base or reference value of the quantity. So for each quantity, the voltage, current, or power, we consider a base value, and then we divide the actual quantity by the base value to have it in per unit. According to this definition, a per unit variable is a unitless variable, yes, because the base quantity must have the same unit, right, with the actual quantity. So the per unit quantity is a unitless variable. There are two major advantages in using a per unit system. 1. The parameters and variables fall in a narrow numerical range. Yes, close to 1. When expressed in a per unit system, this simplifies computations and makes it possible to quickly check the correctness of the computed values. 2. One need not refer circuit quantities from one side to another. Therefore, a common source of mistakes is removed. Yes, when we review the per unit system, also we will check the per unit model of a transformer. In a per unit system, there is no need for transferring quantities from one side to another side. So let's check. To establish a per unit system, it is necessary to select base or reference values for any two of power, voltage, current, and impedance. Once base values for any two of the four quantities have been selected, the base values for the other two can be determined from the relationship among these four quantities. So we have these four quantities: power, voltage, current, and impedance. Among these four quantities, we need to specify base values for two of them. Yes, because we have these two relationships, and when we set the base value for two of these variables, we can calculate base values for the next two variables. So usually base values of power and voltage are selected first, and base values of current and impedance are obtained as follows. So if we select power and voltage and consider base values for them, we can calculate the base value for the current and impedance using these two equations. You know, the I base is equal to the P base divided by the V base, and the base impedance is this one, V base divided by I base, or V base to the power 2 divided by P base. Important equations that we have here. So although base values can be chosen arbitrarily, normally the rated voltamperes and the rated voltage are taken as the base values for power and voltage, respectively. So the base value of the power is the rated volt ampere for a transformer, and the base voltage is the rated voltage of the transformer. So in the case of a transformer, the power base is the same for both primary and secondary. Yes, the power of the primary and secondary, we consider the same value for the base, right? However, the values for V base are different on each side because rated voltages are different. So here, this is the value of the V base, okay, for the primary, and this is the value of the I base, the rated current for the primary. Yes, we write V base 1, I base 1, and this is the base impedance for the primary. Z equivalent one is the equivalent impedance of the transformer referred to the primary side. You remember these two equivalent circuits that we had. Yes, in this equivalent circuit, we transfer quantities to side 1, and in this equivalent circuit, we transfer quantities to the side 2. So, the per unit value of the Z equivalent 1 is the Z equivalent 1 divided by the base value for the impedance, Z base 1. And Z base 1 is here. You can see the definition. Finally, we will have this. What will be the value of the Z equivalent to in the per unit? Let's check. For the secondary side, again, we have these quantities V base 2, I base 2, and this is the value of the Z base. So we have similar definitions. This is the Z equivalent to in per unit format, this fraction, and we will have finally this relation between the per unit values, right? If you transfer this quantity to the secondary, and also we have this relation between the Z base 1 and Z base 2. Finally, we will have this. Therefore, the per unit transformer impedance is the same referred to either side of the transformer. This is another advantage of expressing quantities in a per unit system. So, in a transformer, when voltages or currents of either side are expressed in a per unit system, we have the same per unit values. Okay, this is the I1 in per unit, that is I1 divided by I base 1, I1 divided by I rated 1. We considered the base value for the current equal to the rated one, and we have also these transformations. You can prove that this is equal to I2 per unit, and this is the same for the voltage. When we express quantities in the per unit format, these quantities are the same either for the primary or secondary. So, transformer equivalent circuit in per unit form. The equivalent circuit of a transformer referred to the primary side is shown in figure 26a. Here you can see the figure. Here we have these models for the transformer. This is the model that we refer quantities to the primary. Yes. And this is the model in the per unit system, in the per unit case. So here you can see we have this number equivalent one I1 per unit, but in this case, because these are the same for the secondary also, simply we can write Z equivalent in per unit, and this is the I per unit. V1 per unit, V2 per unit, the value of the voltage for the primary and secondary. Okay, so the equation in terms of actual values is as follows. And how we can rewrite this equation in the per unit form, here we should divide these two sides by VR1 because this model is for the primary side. So we should divide two sides of this equation by the base voltage, that is VR1, rated voltage for the primary. So we will have this, you can do the math, and finally we will have this equation V1 per unit is equal to I1 per unit, Z equivalent 1 per unit, V2 per unit. And we know that this is equal to the Z equivalent 2 per unit. Simply we can write Z equivalent per unit, and the same thing for I. Yes. So using a per unit system, we can have this simplified model. So now let's check the problem and calculate quantities and generate the per unit model for this transformer. First of all, we need to set the base values. What is the base value for the power? Is 25 kVA. So this is the S base. And what is the base value for the voltage of the primary? 220. For the secondary, 440. So here we can calculate the base value for the current of the primary side, that is S base divided by V1, a typo error here. So this is I base 1, S base divided by V1, that is 220, that is equal to this number. And what is the value of the base current for the secondary side? Is S base divided by V2, that is equal to 56.81 amps. So let me modify the MATLAB M file at the same time. Here for this problem, let's check the parameters. This is the S rated, the rated apparent power. This is the base value. So I write S base. And this is the V1 base. Yes, the base voltage for the primary. This is the base voltage for the secondary. So here we have these values. This is the I1 base. Okay, so this is V1, V2. We have these numbers. Actually, these numbers are also the base values. This is the current of the primary, base current of the primary. The base current is the same as the rated one. You know that. And this is the base current of the secondary side, the low voltage or secondary. So if I run the code, here you can see the value of the I base 1 and I base 2. 113.6, 56.8. These two numbers. So what is the value of the Z base 1 is equal to V1 to the power 2 divided by S base. this equation that we had here. This equation for the Z base, yes, 2.62. This equation, I implemented it here. That is equal to 1.93. Oh, the Z base 2 is V2 to the power 2 divided by S base. That is equal to 7.74. Let me check these two numbers. This is the base impedance of the primary. Yes, base impedance of the primary. The unit is in O. And this is the base impedance of the secondary. If I run the code, here you can see the values for the Z base 1, 1.93, and Z base 2 is 7.74. These two numbers. Now let's calculate the quantities using the information that we have for the open circuit and short circuit test. We did similar calculations for the previous problem. So let's just repeat. The equivalent core resistance is the V open circuit to the power 2. The open circuit voltage is 220 divided by the open circuit loss. The value is 74.46. The equivalent core resistance. This is the equivalent core resistance current. Yes, the power of the open circuit, power loss divided by the voltage of the open circuit. That is 2.95. The magnetizing current is equal to this one. SQRT of the open circuit current to the power 2, 9.5 to the power 2, minus the equivalent core resistance current to the power 2. That is equal to 9.02. What is the value of the magnetizing reactance? Is the voltage of the open circuit divided by the magnetizing current. 24.36. I implemented these equations here. This is the equivalent core resistance, right? This is the current of the equivalent core resistance. The unit is in amps. This is the magnetizing current, amps, and this is the equivalent core resistance. The unit is O. This is the magnetizing reactance. The unit is O. And this is the value of the equivalent core resistance in the per unit format. So why we divide this by Z base 1? Because the open circuit test is for the primary side, right? The secondary is open. Here is the case. We have this transformer. The voltage of the primary is 220 The voltage of the secondary is this one. So we have I base 1 here, I base 1 that is equal to the rated one, Z base 1, here we have I base 2, Z base 2, and you know that in the open circuit test, we apply the voltage to the primary, this voltage, to calculate these two quantities, the equivalent core resistance and magnetizing inductance. The secondary side is open. So because we calculated these two quantities for the primary side, we should divide values with Z base 1. Yes, this is the magnetizing reactance per unit. And now let's calculate quantities for the short circuit test. In the short circuit test, we apply this voltage, and this is the rated current. The primary side is shorted, yes, because here in this case, the value of the short circuit current is 55 amps, right? Is equal to this one, the rated number that we have here, the short circuit current that we have. So we can calculate the Z equivalent. Yes, here are calculations, right, for per unit quantities, the equivalent core resistance and magnetizing reactance. Let's check the numbers. Here, this is the RC74. The current is 2.95. Yes, the magnetizing current 9. Yes, this is the magnetizing reactance 24. Yes, the XM in per unit format is 12.58. Yes, correct. The equivalent core resistance in per unit is 38.46. Correct. So this is the Z equivalent for the short circuit test. V short circuit divided by the I short circuit, that is equal to this one. And what about the R equivalent is the short circuit power loss divided by the current of the short circuit to the power 2, that is equal to this one. And finally the X equivalent, we can calculate it using this equation. So let's check the M file. This is the equivalent resistance for the primary and secondary windings. Excuse me, this is the equivalent resistance, this is equivalent impedance, and this is the equivalent leakage reactance. So we should divide these two quantities by the Z base 2. Yes, because the short circuit test is done on secondary side, the primary is shorted. So here we calculate the quantities in per unit form. So this is in per unit, and this is in per unit again. Okay, let's run the code. here you can see the value of the R equivalent per unit 0.04. This one. And what about the leakage reactance? The leakage reactance is 0.078. Yes. So we calculated the parameters of the equivalent circuit in per unit values. And finally, we can draw these equivalent models. This is the magnetizing branch. Yes, we have this equivalent core resistance, magnetizing reactance, and these numbers for the equivalent resistance and equivalent leakage reactance. The V1 per unit, V2 per unit, I1 per unit, I2 per unit, and finally, if we neglect this excitation branch, we will have this equivalent model for the transformer, similar to this one that we have in the right text of the chapter 2, this figure, this model for the transformer. Anyway, B, determine the voltage regulation at full load, 0.8 power factor lagging. So here we have this equation for calculation of the V1 for the full load case. We calculated the voltage regulation in the previous problem, and in this case we are going to calculate the voltage regulation using per unit numbers, right? So here is the model that we have for the transformer, okay? And you know that this is the definition of the voltage regulation. We had the two definitions, right? This is the second one. This is the value of the V2 prime for the rated operation, the amplitude, and this is V1 for the full load operation. So if we consider the V2 prime for the rated operation, this one equal to 1 per unit with this angle. Yes, because this is equal to the rated one. What is the value of the current? The current here, full load. We need to consider the rated current. This is the power factor. So this is 1 per unit. What is the angle? The power factor is 0.8. Yes, lagging. So you know that 0.8 lagging is equal to 36.8. So negative 36.8. We can calculate V1 for the full load operation using this equation. Yes, V1 for the full load operation is the V2, that is 1 per unit with this angle, plus the current times the impedance of this right branch. So this is the value of the V1 for the full load. you can replace the numbers. The voltage regulation will be equal to 8%. Yes. So let's check the numbers. Also, I think we have the solution of this problem. Yes. Problem 14. This is the equivalent core resistance. Yes. 38.47. The magnetizing reactance. The equivalent resistance and the leakage reactance. Yes. The value of the voltage regulation is 8%. Okay. So now let's discuss this approximation, this important equation that we have here. We used this equation to calculate the exact value of the voltage regulation. What is this equation? This equation is we write V1 for the full load operation is equal to, excuse me, V1F is equal to V2 per unit, that is equal to 1, this is the angle 0, plus the I per unit, this is 1, and we have one angle here. So we can write cosine of phi, this is the power factor, right? Minus j times sine of phi times this one. This is the R equivalent. Yes, R equivalent in per unit format. And this is plus J X equivalent in per unit case. So here, because we considered this phi angle, this is the phi, right? Like this, we also wrote the value of the current like this. So this is negative phi. Actually, the phi is this angle. Yes, the phi is the absolute value, right, of the angle between the current and the voltage. Because sometimes we have lagging, right, power factor and leading power factors. So you can consider the angle in its algebraic form, positive and negative sign, or just you can consider the absolute value of the angle, the geometric form of the angle between the voltage and current. But you must consider proper sign here. Okay, so in this case, if we consider a lagging power factor and inductive load, so the value of the phi, if I consider it equal to 36.8, this will be the equation. Okay, so we have this negative sign here. If we multiply these two complex numbers, we will have cosine of phi, yes, times R equivalent. I don't write the per unit. So then we have this multiplication. This is plus sine of phi times X equivalent, plus we have J times this cosine of phi times x equivalent minus this product. Yes, this is the sine of phi times r equivalent. This is plus 1. Okay, so when we calculate the voltage regulation, we need to take the amplitude of this complex number. Yes, this is the real part and this is the imaginary part. But because the value of the R equivalent per unit and X equivalent per unit, you can check these numbers, right? Are very low. Yes. And in this case, if we neglect the imaginary part, simply the amplitude of V1 for the full load will be equal to this one. And considering this fraction, you can calculate the voltage regulation. The voltage regulation simply is this term, this one. So let's check that if this approximation works good or not. Let's calculate the voltage regulation using this approximation, neglecting this part. So here, if I write in the MATLAB, here is the procedure for calculation of the voltage regulation using the exact equation. Yes, the second method that we discussed, this is the value of the current, okay, 1 per unit. So this is the full load current in per unit format. This is the value of the voltage drop. This is in per unit. This is the voltage of the primary for full load operation. Voltage of the primary for full load operation. What is the value is equal to 1 plus voltage drop. And this is the voltage regulation. We need to calculate the absolute value of the V1 for the full load. Okay. So this is the voltage regulation. And this is calculation of the voltage regulation using this approximation. So here, this is the cosine of phi and this is sine of phi. The sign here is plus because we have a lagging power factor. So if I run the code, as you can see, the value of the VR, the exact value is 8. VR approximation is 7.93. That is very close to this number. And this is a good approximation considering the assumptions and conditions that we discussed. So for the leading power factor, you should consider negative sign. Yes, because we considered the phi as the angle between the voltage and current phasors. So, okay, so using this approximation, we can derive these two equations. When we have maximum voltage regulation, we discussed that in this slide, the maximum voltage regulation occurs for this condition. And here in the new case, let's check. The voltage regulation is equal to this one. Yes, you can rewrite this equation into this form. Yes, the amplitude here also I can write plus or minus, but because we know that the maximum voltage regulation occurs for an inductive load, I consider it plus here, and this is minus finally. So the voltage regulation is the amplitude of the Z equivalent in per unit form times this. So when this is maximum, when the value of the phi angle is equal to the angle of the internal impedance of the transformer. Yes, this condition. Okay, so this is the case when we have maximum voltage regulation. Consider that in this figure, theta 2 is a negative number, right? Here we used absolute values. And when we have zero voltage regulation, the zero voltage regulation occurs for a leading power factor, a capacitive load. So when this is equal to 0, you can write this equation. The tangent inverse of phi must be equal to this one. So in this case, we have 0 voltage regulation. So how we can investigate these two important points? Here, for the previous problem 13, I wrote this code. Here I changed the value of the phi at the end of this M file. I calculated the Z base for the high voltage side, and this is the VR approximation. Okay, to compare these methods, we calculated the voltage regulation using two methods in problem 13 and one new method in the problem 14, this equation. So here in this for loop, I change the value of the phi from negative 90 degrees to 90 degrees for a pure inductive load to a pure capacitive load. This condition, suppose we have this V2, I want to change the phi angle, this angle, from negative pi divided by 2 to pi divided by 2, pure inductive load to a pure capacitive load. And here I calculated the voltage regulation using the first method of the problem 13, the second method, and the approximation that we have here. In this case, because I considered negative and positive values for the phi, I used this equation. Yes, so this equation supports both inductive and capacitive loads because we considered the sign in the value of the phi. But if you consider phi as a positive number, you should consider this plus or minus sign manually. So let me run the code. Here you can see the variation of the voltage regulation as a function of the load impedance angle. Yes, here we have maximum regulation that occurs for an inductive load, zero voltage regulation, yes, here occurs for a capacitive load. And for pure capacitive load, we have minimum voltage regulation. So let's check the equations that we derived here. The maximum voltage regulation should occur here. So what is the angle of this one? What is the angle of the Z equivalent? This is the Z equivalent. Okay, a complex number. I'm going to calculate its angle times 180 divided by pi, 68.9. So here negative 68, right? 0.9. Here we have maximum voltage regulation. You can see the negative sign here. And let's add a new point. I want to find the zero voltage regulation when the value of the y is 0 is here, right? When the angle of the load impedance is 22.4, we have 0 voltage regulation. This condition, let's check this condition. Angle, or this is a ton of R equivalent high voltage divided by the X. Okay, this condition for the zero voltage regulation. The angle is 21.1. Yes, that is close to this one. Here, because we use three different methods, as you can see, we have a slight, right, difference between these curves. The blue one is the first method of the problem 13. Then we have the next method, and finally this approximation. This orange one is for the approximation. So let me delete this. Let's run again. This one is for the approximation. So here the zero voltage regulation occurs for this angle 21. Okay, 21. So we have a slight difference between these graphs, but okay, this is a good approximation, and we can find these two important relations using this equation. Anyway, you can repeat the same calculations for the voltage regulation. Finally, part C, draw the phasor diagram for the condition B. So here, for this problem 14, how we can plot the phasor diagram? Because the quantities are in per unit form, we can set the scale of these phasors equal to 1. And here we can generate this nice vector diagram. Quantities are in per unit. You can see this is the I1 full load. This is V2 rated, that is 1 per unit. Its angle is 0. This is V1 for the full load. This is the value of the voltage drop. Perfect. You can generate this phasor diagram using, right, these two functions. Okay, so let's go for the next problem. Problem 15. A single phase 10 kVA 2400 to 120 volt 60 Hz transformer has the following equivalent circuit parameters. This is the Z equivalent for the high voltage side. This is the equivalent core resistance for the high voltage side. The magnetizing reactance, okay, is also given for the high voltage side. Okay, so we have the model of the transformer for the high voltage side. A standard no load and short circuit tests are performed on this transformer. Determine the following: no load test results, short circuit test results. Yes, because we have a standard tests, we know that the open circuit test is done on the low voltage side and the high voltage side is open in this test. So first of all, let's calculate the current of the high voltage side and the current of the low voltage side. Here you can see the numbers, the current of the high voltage side. Let me check. No, I don't have M file. We can write M file for this problem, but it is not too complex. Yes, this is the current of the high voltage side, 10,000 divided by 2,400, 4.166. Just let me check the numbers. 4.16 amps. The current of the low voltage side is S divided by the voltage of the low voltage side. This divided by 120, 83.3 amps. This is the transformer turns ratio. As you can see here, we have a high turns ratio that is equal to 20. Okay. So how we can calculate the value of the current in the open circuit test? The voltage of the open circuit test is equal to 120 because the test is a standard. We apply the rated voltage, right, to the low voltage side. The high voltage side is open, similar to the previous problems that we had. And to calculate the value of the current in the open circuit test, we need to know the value of the equivalent core resistance current and the magnetizing current. So to calculate these parameters, we need to know the value of the equivalent core resistance and magnetizing reactance at the low voltage side. So these two numbers are given for the high voltage side, 64 kilo ohm and 9.6 kilo ohm. So we can refer these quantities. What is the value of the RC at the low voltage side? Is 64 E3 divided by 20 to the power 260. This number. And what is the value of the magnetizing reactance? Is equal to this one, 9.6 E3, that is equal to 24 ohm. So Then we can calculate the equivalent core resistance current. This is the voltage of the open circuit divided by the RC divided by 160.75. What is the value of the magnetizing current? 120 divided by 24, that is 5 amps. This is the value of the open circuit current. Yes, SQRT of IC plus IM, right? Both to the power 2. And finally, the power of the open circuit test is V open circuit to the power 2 divided by RC. So let's check this. 120 to the power 2 divided by 160 is equal to 90 watt. So we calculated these quantities, right? Considering these numbers, we should refer quantities for the low voltage side. And what about the V short circuit, I short circuit, and P short circuit? The equivalent impedance is at the high voltage side. So we don't need to refer it because we know that in the short circuit test, we short circuit the low voltage side and perform measurement on the high voltage side. So in this case, the value of the short circuit current is equal to the rated current of the high voltage. Yes, this number. The power loss in the short circuit test is the R equivalent times the I short circuit to the power 2. This is the R equivalent times the I short circuit. This one to the power 2. Let's check. 5 times 4.166 to the power 2. 86.8 watts. What is the value of the voltage of the short circuit? Is the amplitude of the impedance, the equivalent impedance at the high voltage side times the short circuit current. So this is the value of the short circuit current. Let me cut this. Yes, this is the order. This is the amplitude of the equivalent impedance at the high side. So what is the absolute value of the 5 plus 25J? 25.49 times 4.166 is equal to 106.2. So we calculated these, right, parameters knowing the equivalent circuit parameters of the transformer and rated values, right? Rated voltage, rated currents, and the rated power. Okay, so let's go for the next problem. Problem 16. A single phase 100 kilovolt ampere 11,000 to 2200 volt 60 hertz transformer has the following parameters. The value of the resistance of the high voltage winding is 6 ohm. The value of the magnetizing inductance is 160 Henry. The value of the resistance for the low voltage winding, the value of the core resistance, and leakage inductance for the high voltage winding and the low voltage winding. Obtain an equivalent circuit of the transformer. A referred to the high voltage side, B referred to the low voltage side. Okay, so The first step is calculation of reactances. Yes, here we have the value of the inductance for the magnetizing inductance and leakage inductances. How we can calculate reactances? You know that the value of the reactance for an inductor X is equal to omega L. Omega is 2 times pi times F. The value of the omega is equal to 2 pi times 60 hertz is the frequency of the transformer, 377 radian per second. And what is the value of the turns ratio? Is this one, 11,000. That is equal to 5. So a to the power 2 is 25. So first, let's calculate the parameters of the equivalence circuit considering the high voltage side. Then we derive parameters for the low voltage side. The magnetizing reactance for the high voltage side is omega times Lm for the high voltage side. That is equal to this number. You can do the math. The value of the leakage reactance for the low voltage side is 1.2, and the value of the leakage reactance for the high voltage side is 30.15 according to these numbers that we have here. So how we can transfer these quantities from the low voltage side to the high voltage? We need to multiply them by a to the power 2. So the value of the resistance of the low voltage winding referred to the high voltage side is 7, and the value of the leakage reactance of the low voltage winding referred to the high voltage is 30.10. Also, we can calculate, right, the equivalent resistance for the high voltage side. For the high voltage side, we have the numbers. We don't need to do any change. The equivalent resistance for the high voltage side is the resistance of the high voltage winding plus the resistance of the low voltage winding transferred to the high voltage side. 6 plus 7. And this is the value of the leakage reactance, the equivalent leakage reactance, that is equal to the leakage reactance of the high voltage side plus the leakage reactance of the low voltage side referred to the high voltage. That is equal to this one. And we have the value of the R core. Yes, this one for the high voltage side, and the value of the magnetizing reactance for the high voltage side. Yes, these two numbers. So here in these three boxes, we calculated all parameters needed for the model of the transformer referred to the high voltage side. And what about the low voltage side? Yes, we can do these calculations and calculate the resistance of the high voltage winding referred to the low voltage side. That is the R high voltage divided by A2 equal to 0.24. The value of the leakage reactance, yes, of the high voltage winding referred to the low voltage is 1.2, and we can do these calculations similar to this one. Also, we need to refer the equivalent core resistance and magnetizing inductance to the low voltage side. Yes. So here we have this typo error. This is low voltage. Okay. The equivalent resistance for the low voltage side is the resistance of the low voltage winding plus the resistance of the high voltage winding referred to the low voltage side. Similar to this one for the leakage reactance, and we need to calculate the equivalent core resistance for the low voltage side and the magnetizing reactance for the low voltage side. Let me check numbers. Here we have, right, for the problem 16. As you can see, we have the RC1 for the high voltage side. We have these numbers 125, yes, 60 kilo ohm, yes, this the unit here is ohm. This is 13, yes, the value of the R equivalent one, and this is 60.3, yes. What about the low voltage side? 5, 2.4, yes, this is 5 kilo ohm, 2.4, and the value of the R equivalent is 0.52. Yes, finally 2.41. 2.41. Yes. So we did these calculations correct. One important point that you can realize from this problem is this one. The value of the resistances. Yes. When we transfer the resistance of the high voltage winding to the low voltage, this number is close to the resistance of the low voltage winding. Yes, this is the actual value of the resistance of the high voltage winding. The resistance is higher, but when we transfer it to the low voltage side, the resistance is close to the resistance of the low voltage winding. And we have this for leakage reactances also, right? So this happens if we have a well designed transformer. In next courses in future electrical machines design courses, when you design single phase or three phase transformers, you will check this. Okay. So if you have a transformer that is well designed, this should happen. Yes. When you transfer quantities, the resistance of the windings and leakage reactances to one side, you right should have close numbers. So this important point that we can realize from this problem. So let's go for the next problem. Problem 17. A single phase 440 volt 80 kilowatt load having a lagging power factor of 0.8 is supplied through a feeder of impedance 0.6 plus J 1.60 and a single phase 100 kilowatt ampere 220 to 440 volt 60 hertz transformer. The equivalent impedance of the transformer referred to the high voltage side is 1.15 plus J 4.5 ohm. A. Draw the schematic diagram showing the transformer connection. B, determine the voltage at the high voltage terminal of the transformer. C, determine the voltage at the sending end of the feeder. So here we have this case. Yes, the circuit that you can see here. In this problem, I think we have a typo error. I will explain the reason. This is the rated voltage of the primary side of the transformer, 220, and this is the rated voltage for the secondary side. Yes. In this case, we connect the secondary side to the load. Here we have this load, 80 kilowatt, and the value of the power factor is 0.8, lagging. Yes, this is the load current equal to the current of the high voltage side. In this case, that we have this voltage ratio. This is the equivalent impedance of the transformer at the high voltage side. This is the feeder, and this is the voltage of the feeder. This is the voltage of the transformer for the low voltage side. So in this case, let's do calculations. Okay, here, what is the value of the load apparent power is equal to the load active power divided by the power factor. 80,000 watt divided by 0.8 is 100 kilovolt ampere. This is the same as the rating of the transformer. Yes. What is the value of the load current? Is equal to 100 kilovolt ampere divided by the rated voltage of the load, that is equal to the rated voltage of the transformer, the high voltage side. The value of the current is 227. So here for this problem, we have these numbers. The rated apparent power, the voltage, right, of the primary, rated voltage of the primary is 220. Let's write this V1. This is V2. Okay. That is equal to 440. This is the Z equivalent 2. In this case, we have the Z equivalent for the high voltage side. In this case, the high voltage side is the secondary side. This is the impedance of the feeder. Yes, feeder impedance. The unit is ohm. This is the transformer internal impedance. Internal impedance, right? The unit is ohm. And this is the load active power. Load active power. The unit is watt. This is the load power factor. Load power factor. Yes. And this is the load voltage. That is the same as the V2. So here is the transformer turns ratio, our outputs. Yes. This is the transformer turns ratio, V1 divided by V2. Transformer turns ratio. What is the value of the load apparent power? Is this one. This is load apparent power. volt ampere. This is the load current. The power factor is zero point 0.8, is lagging. I consider this negative sign. This is the amplitude of the load current, or the current of the secondary side of the transformer. So in this case, what is the, this is the load current, this one. Yes, we can calculate the load current using this equation. And in this case, when we have this load current, we can calculate voltage drop here, right? The voltage drop that we have on this equivalent impedance. So how much is the value of the voltage drop? Let's check. This is the V drop is equal to the value of the Z equivalent to times the the load current, the current of the high voltage side, right? Z equivalent times this current is the voltage drop here, and the voltage that we have here is this voltage drop plus the load voltage. So this is times the load current plus the V load. V load is equal to, right, this one. The angle is 0. I considered this reference angle for the V load. This is VL, and this is the current IL, right? A lagging power factor of 0.8. The power factor is 0.8, this condition. So this is the value of the V load plus this voltage drop. And we have, this is the voltage drop, and this is the value of the voltage here for this point. The value of the voltage here. Let's call this, right, V star. So when we have this voltage, we can transfer it to the low voltage side. So this is V star. How we can transfer it to the low voltage side, or V1 full load? The V1 full load is equal to V star times A. So let's run this code. What is the error? V load, we don't have this variable. Okay, I should define the V load here. This is the load rated voltage. Yes. So if I run the code here, we don't have Z equivalent. This is Z equivalent to, Yes. So this is V1 F. What is the amplitude of this? The voltage of the low voltage side for the full load operation is 712. This number, 712. This is the turns ratio. This is the load voltage, the current, and this is the voltage of the low voltage side for the full load operation. But this is not logical. Yes, it's not logical because the value of the rated voltage of the primary winding is 220. So in this case, the amplitude of the voltage is much higher than the rated voltage. So in this case, we have a high amount of copper loss. So if we consider this number 2200 for the rated voltage of the primary, so we will have this equivalent circuit, right? So in this case, the voltage of the primary is right, high enough, right, more than the voltage of the secondary. And here, this is the primary side is the high voltage side. Yes, we connect the load to the secondary side. This is the equivalent impedance of the transformer. We have it for the high voltage side. And this is the high voltage, right, terminal. We need to calculate its voltage for the part B. Yes. So this is the case 2. In this case, the transformer turns ratio is 5. The load voltage is this one. This is the load current. This is the current of the high voltage side. Yes. When we know the value of the current here, we can transfer it to the primary side using this equation divided by A, transformer turns ratio. And this is the value of the voltage for the part B, the voltage at the high voltage terminal of the transformer, equal to this number. Okay, this is the V2 prime. Actually, this is the load voltage transferred to the primary. So for the primary side, we have 2.2 kilovolt, this voltage. So HV, this voltage is this voltage drop plus this one. Okay, so we have this case. This is the load voltage referred to the primary plus the current times the internal impedance of the transformer. So we will have this value. This is logical. Yes, this is logical. And the voltage of the feeder, yes, for the part C, the voltage at the sending end of the feeder is equal to this one. We need to add up the impedance of the feeder and calculate the voltage drop on the feeder also. Here, this summation. So let me write the code here. This is the second case. If we consider 2.2 here, this is the value of the current. I1 full load is the load current divided by A. So this is the full load current for primary side, and this is the V1 full load or V high voltage, right, for the rated current. I can write this is better. V1 full load, we know that the primary side is the high voltage side, that is equal to the referred value is equal to 2.2 kilowatt plus the current referred to the primary Z equivalent. And what is the voltage of the feeder? Is this one. The feeder voltage for the full load operation is this current. Just we need to add up the Z feeder. So let's run the code and calculate the amplitudes here. the amplitude of this voltage is 2368, this number. What is the value of the feeder voltage? The absolute value is this one, 2436. Yes, this is logical now. Maybe a typo error that we have for this problem 17. Also, what we don't have the solution, you can check the calculations for this important problem. Yes, maybe we have a typo error here. How we can plot the phasor diagram? Let me copy the code here. We can plot this. So let's generate plots one by one. Comment this part of the code. You can write, use Control R to comment and Control T to uncomment the code. This is the first phasor. The load voltage referred to the primary. Yes. This is the V load, V1 load. This is the load voltage referred to the primary, 1E minus 3. Let's consider this scale. The next one, let's generate this with another color. The V1 full load. This is V1 full load. Yes. Then we have the feeder voltage, red. This is the feeder voltage full load. Okay. So this is feeder. Yes. And what about the current? This is the I1 full load. Let's use this scale and check. Yes, this is the current phasor. Use another color, green. Also, let's plot the voltage drops. How we can plot voltage drops? We have one voltage drop here from this to this one, 1E minus 3. Let's use this scale. This is the voltage drop that we have on the internal impedance of the transformer. Yes, this voltage drop, and this is the voltage drop that we have right on the feeder. So yes, this one. So actually this is the feeder voltage. Another color, maybe we can use the, oh yes. So you can see the graph. Let's use M again. Yes. So this is the phasor diagram in this case. This is the, you can also set the tags. This is I1 full load. This is the voltage drop on Z equivalent. This is voltage drop on Z feeder. Perfect. We can generate this nice phasor diagram. This is the I1, the load current transfer to the primary for full load operation. This is the V1 load, the load voltage transferred to the primary. Also here you can realize the importance of using per unit system. We don't need to adjust these scales to generate the phasor diagram. This is the V1 full load, this blue vector. So let's place this here. This is the feeder voltage. This is the voltage drop on the feeder impedance, and this is the voltage drop on the internal impedance of the transformer. So here we have these two voltage drops. Anyway, you can repeat the same analysis and generate this phasor diagram also for this problem. Also consider that we solved this problem considering two cases. Yes, it's enough for this video. Let's continue solving the next problems in the next video.